Okay, let's start with chapter 8. In previous lectures, we accomplished chapter 7, in which we defined different kind of flows, and we talked about different cross sections, and also we defined hydraulic radius and hydraulic mean depths as the main important geometrical characteristics of cross sections in natural channels. So in this lecture and in that lectures, we divide flows in uniform and varied flow, and also in terms of time, we divide flow in steady and unsteady flow conditions. And as I mentioned in previous lecture, this lecture we are going to see how we can calculate main characteristics of flow in uniform flow condition. So let's get started with computations of uniform flow in natural channels. Uniform flow, as we already discussed this definition, all characteristics of flow are same along the whole length of flow. For example, you see here flow along here to here, and we have different characteristics along the flow. For example, V1, assume this is our first section. Here we have one section, and here we have another section, and there is a distance between two sections. In first section, velocity or average velocity of flow in the section is V1. Therefore, you can calculate based on the geometry, you can calculate A1, which means the area of the cross section. And we have V2 and A2 in section 2. If the flow is uniform, we said that V1 should be equal to V2 and A1 should be equal to A2. This is definition of uniform flow. However, here you see an example of non-uniform flow, which also we called it varied flow. Yes, you see here we have, for example, V1 and A1, V2, A2. It is clear that there is a change in the depth of flow. Therefore, we have definitely change in the velocity in the area, and perhaps we have change in the velocity. Even when one of them varies, therefore we can say it is not uniform flow. So in this lecture and in chapter 8, entire chapter 8, we will talk about uniform flow condition, as you see here, uniform flow condition. As we told, in uniform flow condition, we have V1 equals to V2 and A1 equals to A2. Can you guess what does it mean when we say V1 velocity is here equals to velocity here? Assume there is 100-meter distance between 2 points. What does it mean? When velocity at two different points are constant, what does it mean?
It means area is equal.
No. Constant velocity means there is no acceleration, yes? There is no acceleration. So when we say A1 equals to A2, what does it mean? Assume cross-section at upstream equals to cross-sectional area at downstream. What does it mean? It means here you might cannot answer, because here when the cross-section is constant between 2 points, we say the channel is prismatic. Therefore, when we say V1 equals to V2, it means there is no acceleration. It is in that case, we also say this is a steady uniform flow. There is no acceleration, and prismatic channel is a channel when the geometry is constant along the river. Geometry of cross-section is constant, we say prismatic channel. So this is actually a condition to have uniform flow. If the channel is not prismatic, if there is a change in the shape of the cross section, definitely there is non-uniform flow. And the same comes from the definition of the for V1 equals to V2. It's the definition, but the prismatic channel is the condition. Without prismatic channel, we cannot have uniform flow. So assume this this river, and we have flow, water moving from upstream to downstream, and we said that V1 equals to V2. So my question here is, why doesn't the flow accelerate? Why along the channel there is no acceleration? Can you guess? Assume that you are driving your car and you move with constant velocity. Why you think that you don't increase or decrease your velocity and you have constant velocity? Means why you don't have acceleration? What happens when you are driving? From that point, you might be able to answer in a flow of a river. There is no idea. In order to be able to answer that question, you might use this formula, Newton's second law. No acceleration means what? No acceleration means A equals to 0. Therefore, m times A, moving water, has a mass, okay? A body of water moves within a river. It has a mass. It is not 0, but acceleration is 0. When there is no acceleration, it means that sigma f equals to 0. The reason why the follow cannot accelerate or moves or motion is with a constant velocity is that the net force, sigma f, the net force, or is 0. We say this is what? This is force balance. Force balance means that any forces acting on the motion of flow cancel out each other. You know, so there is some force, forces compel the water to move downward. There are some forces that resist against motion, okay? When the net force equals to 0, it is called force balance, and this is why A is 0. So here we can say that there is no net force or force balance acting on an object if all the external forces cancel each other out, then the object will maintain a constant velocity. Is this sentence familiar to you? Have you ever seen this sentence anywhere? You don't remember? This is first law of Newton. Newton's first law, and you should know it from your high school knowledge. Okay, I hope at least you are able to answer this question. Don't write, please don't send any message to me from chat box because I just see my screen, my PowerPoint file. As you see my screen, I don't see the chat boxes, therefore don't send any text message from chat box. If you want to talk, just start to talk. So now the question is that which forces acting on flow or on a body of water in a river? Any idea?
Gravitational force.
Yes. Gravitational force. You remember that last session I said that the main force for motion of water in natural channels is gravitational
Wind.
force.
Some wind.
Wind could be good, could be wind also. These are positive force. It means these are the force that that acts to have motion, and we have resistance force everywhere. When someone asks you which forces we have, definitely you have friction force. In any motion there is friction. Always use it. Always. Which forces we have? If you cannot remember anything, at least you can say there is friction force. Always we have friction. Okay, so we have friction force also. So for gravitational force, who said gravitational force? Who said?
I said it.
Your name?
Mesa.
About wind force? Who said wind
I
force?
said
Your name?
Murat.
Family name?
Murat Yıldız.
Yes, okay. So let's neglect from wind source. Okay, assume that wind, definitely when we have wind, it acts on a force, but sometimes there is no wind. Okay, and we assume that water moves only with the gravity force, and there is a frictional force again against motion. Therefore, gravitational force of the water is equal to friction drag. For frictional force, again motion of water, we say drag force or friction drag along the channel. You already know about drag force from fluid mechanics. When you remember that we even in hydrology we discussed the drag force about. Do you remember when a droplet, a raindrop falls, there is drag force from air. Resist again the motion of raindrop, and in that way you remember we defined maximum velocity of raindrops. So we have equality between the gravity force and between drag force. Therefore, we can say that there is no acceleration because sigma f equals 0, and this is why velocity is constant along the channel. Now I'm going to show you this force balance in more details. Okay, what is gravitational force, what is drag force, and how we can express them using mathematical formula. Let's assume this is our channel, okay? This is bed, and there is a flow motion from upstream to downstream. You see the slope of the channel equals to the angle equals to theta. Okay, let's define first about slope. What is the slope of this channel? The slope of this channel equals to sine of theta over cosine of theta, because the slope of channel equals to slope of the bed. Now one question, where is our surface? This is our free surface. Yes, free surface. You see our rectangle here. This is our free surface. Do you think that, the question is, do you think that the surface, water surface profile, this is water surface profile, should be, do you think that water surface profile should be in parallel to bed? Because I'm going to find the slope of the channel. And do you think that the slope of the bed equals to slope of the water surface or free surface? Any
Yes.
idea?
Yes.
Yes. Why?
Because we have uniform flow. So we shouldn't change the area, cross-section area.
Yes, that's right. Thank you. Thank you. Because if you think about only depths, cross depth is one characteristic of the cross-sectional area. This is my, at point A, this is my depth. Yes, this is my depth. At point, for example, here, D, my depth is here. If there is a the spotter surface is not in parallel with the bed, D1, the depth of flow at A will be vary and will not be the same with D2. Therefore, there is no uniform flow. So the first rule, or one of the main important rules in uniform flow, never forget it, free surface or water surface is always in parallel with bed slope. Never forget it, it is in uniform flow. And we said that when the channel is prismatic, there is no acceleration also. It is also called steady uniform flow. Okay, so when I ask you what is the slope of channel, you can therefore this theta equals to assume there is a horizontal line here. There is a horizontal line here, and this theta equals to the angle of the horizontal angle of water surface. So you can calculate slope as sine of theta divided by or over cosine of theta. And in natural channels, generally, this means tangent theta. Yes, this means tangent theta. Am I right? Sine of theta over cosine of theta
Yes.
means tangent theta. In natural channels, slope are very low, very, very low. This theta is commonly less than 10 degree. Therefore, we, instead of saying tangent theta, we can say that S equals to sine of theta. Okay, this is another rule, or S approximately equals to sine of theta. So from now, when I say S, it means the slope. So this is our slope, and we are going to derive drag force and also gravity force. So we defined the slope. We also see hydraulic grade line and energy grade line. These are something that you already know it from your fluid mechanics. In natural channels, hydraulic grade line shows water surface level. And you remember that energy, total energy, was the summation of elevation plus P over gamma and plus what? V square over 2G. This is P over gamma for us, P over gamma, depth of channel, and we have V square over 2G. What is V square? For example, V here is average velocity of this cross section. Average velocity over 2G. Therefore, it is called kinematic head. And if you consider energy grid line, you will see that energy grid line always is in parallel to water surface. Why? Again, you can say because V is constant. Here is constant, here is constant, here. Therefore, V square over 2G remains constant along this river. So the second definition, in uniform flows, river bed or channel bed, hydraulic grade line, which symbolize what? Water surface or free surface, and energy grade line are in parallel. This is our second rule. So now we know the hydraulic grade line, energy grade line, and channel slope. So in order to calculate friction force, what we need, again, you should think about fluid mechanics knowledge and how we calculate friction. in chapter 1, fluid mechanics, we talked about viscosity and friction comes from what? Shearing stress, yes? So friction force creates shear force. And can you guess how we calculate shear force? Or friction force easily from physics knowledge you can say it. Okay, you know that force is the multiplication of stress, shear stress times to what? To area, cross-sectional area. Assume now we consider only this block or element of water, A, B, C, D. And we assume that this element moves downward, okay? So we are looking or we are calculating friction force. We said this is drag force, and this force is a result of shear stress. So I need to know shear stress at the where? At where? Any idea? At anywhere that water is in contact with channel. Put your hand on your desk now. Put your hand on your desk and move it. Just there is a friction, just any places that your hand is in contact on your desk, not at the above the hand, yes, only below hand. But in a water cross section, we have a place that water is in contact with channel or channel bed and channel banks. If it is, for example, a trapezoidal channel, assume the cross section in a trapezoidal channel, and we have locations, some places that water is in contact with bed, with channel. What we call that length?
Wetted perimeter.
Wetted perimeter. We called it wetted perimeter. Your name?
Erdem Çetintaş.
Therefore, the wetted perimeter is the place that shear stress acts on it from that place on the water, okay? So from the definition of force, we know that stress should be multiplied by area. Force equals to stress or tension times area. Wetted perimeter, as the name says, it is a perimeter. But when we assume this this box of water, this element of water, our wetted perimeter by multiplying to delta x or distance of the water element changes to wetted area. Yes. So we have 1 delta x from here to here, and we have a wetted perimeter that symbolizes the cross section. Therefore, this is my area, P wetted perimeter times delta x, and I have shear stress. This is a parameter that depends on the physical condition of natural channels, depends on the material of the bed, depends on if it is a canal, depends on the construction matter. If the canal is from the stone, if the canal is from concrete, yes. If there is some grasses within the canal, friction factor. This is something like friction factor. It varies. Therefore, so far we know weighted parameter because we know the cross section, we know delta x. We assume that this delta x a very small length of a channel, delta x, a very small length. And if we know the shear stress or the this factor, this friction factor, we can calculate shear force. Is it clear now? What is shear force? It should be, yes.
Yes.
The other force was what?
Yes.
We had two forces. The one was drag or shear stress, the shear force. The other force was gravity force. Let me check that now. This is the time. No. Okay. Let's talk about weighted perimeter. I also explained it. P is weighted perimeter. And the time is for calculation of the gravitational force. Looking at this water element, okay, element A, B, C, D, it has the weight of W, yes? It has the weight of W, We assume that this block of water has the weight of W. So can you tell me what is the gravitational force acting on this water element? Very easy question, very easy. And if you answer, you got 1 point. Think about it.
Hocam, I think it's W.
W, it's weight, not gravitational force.
W times cos theta is the gravitational force.
Who answered?
Buse.
Unfortunately, no. You should times by sine of theta, not cosine theta. Gravitational force acting what? Last session, I talked about it half over. The gravitational force is the force that is in the direction of what? Direction of flow. Why? You have motion because of gravitational force. And you look here. You see this W sine of theta is in the direction of flow. Yes, Buse? I think you never forget it. Gravitational force is the force in the direction of flow. It is W sine of theta. So what is W? How we calculate W? Okay, we know the gamma of water, and you know that weight or gamma equals to weight over volume. Weight over volume. So we have this element, the length of element delta x is at hand. The depth also is known. A from the distance from A to B, the distance from C to D is at hand. Therefore, you can calculate volume, and also you know the width of the cross section, width of the channel. Width is the length into this monitor. This is perpendicular to you when you are looking. This is width of the channel. So we assume that the width is 1 unit for unit meter of the cross section. Okay. Now all these calculations are based on a unit width into the monitor. So I can calculate easily the weight. This is my weight, gamma A cross-sectional area. If you assume that width is 1, therefore cross-sectional area, instead of A, you should write the depths, just depths. But here A means depth times, if it is rectangular cross-section, equal A times width. A equals to width times what? Flow depth. Therefore, this is my my weight W, and times sine of theta. It is gravitational force. So what we said we have force balance. Yes. We have force balance because this is uniform flow, force balance. And we said that sigma F, or net force, equals to 0. This is my sigma F equals to 0. So you know that weight, gravitational force is in this direction, but friction force, as shown here, is against motion. This is why we use negative sign for shear force or drag force. Therefore, in total, force balance in natural channels are written like this: gamma, water density, area, cross-sectional area, delta X, the length of this element. Okay, here is an element, and now instead of delta X, for entire length of channel, assume you are calculating for 100 meter of the length of the channel, or your uniform flow is in a channel, in a canal with 1000 kilometer. Just write here 1000 kilometer times of sine of theta. What is the sine of theta? What is the sine of theta?
Slope.
Yes, sine of theta is slope. Even S equals to sine of theta is the slope of the channel, minus what? This is our shear stress, tau. You know it. Tau, in fluid mechanics, you remember we used Newton viscosity rule in order to calculate tau in Newtonian fluid, but this is completely in fluid mechanics. We need another definition to calculate shear stress. Okay, shearing stress in natural channels. Okay, this is our shear stress. P is weighted parameter. We know how to calculate it based on those formula given in chapter 7, or based on the formula that we last session studied in order to calculate weighted parameter in any kind of irregular cross sections. And again, this is the length, and it should be 0. Let's continue. And before saying this, gamma is, do you know the value of gamma for water? Do you remember? 10 to the power of 4. You remember 10 to the power of 4 Newton per cubic meter. It is at hand. Cross-sectional area, it is at hand. Delta X, we defined it. Here is, for example, 1 or small, or a length of river at hand. Sine of theta, from geometry of channel, it is at hand. Weighted parameter at hand. Delta X at hand. Therefore, what is unknown here? The only unknown is shear stress. And we can now calculate shear stress from this equation. Therefore, shear stress equals to gamma times A over P sine of theta. Is something in this formula familiar to you? What?
Hydraulic radius, A over P.
A over P is hydraulic radius. What was your name?
Kürşat Yol Koçlar.
Kurşat Yol Koç. Okay. Okay, as Kurşat said, we know A over P, which equals to hydraulic radius. And you see here that if we replace A over P with R, or RH, hydraulic radius, the formula would be very easier to memorize it. Tau equals to tau, or tau is shear stress in natural channels when the flow is uniform. Look, never forget our first assumption for uniform flow. Tau equals to gamma, water characteristics, density of water, R, cross-sectional characteristics, S slope characteristics. These two are geometric characteristics and what? Water characteristics, density, which is, as I told, commonly 10 to the power of 4. So we know now how to calculate our shear stress. Tau 0 equals to gamma RS. Here you see that shear stress is a function of channel slope, or thus energy loss is a function of a slope. Do you agree with this? Definitely yes. So we here see that shear stress. So far I said you one important rule in uniform flow. The first one was channel bed, hydraulic grid line, and energy grid line are in parallel with each other in uniform flow. This is first. This is the second one. Shear stress is a function of channel slope based on this formula, and therefore energy losses is a function of slope. Yes. Okay, it is there is direct relationship, or I mean that is there positive relationship or negative relationship between the energy loss and the slope. You see that if slope increases, tau increases, and you see that tau is what? Tau is in positive direction with shear force, we know it. When tau increases, shear force or friction force increases, and therefore energy friction force when increases, energy decreases, and energy we will have energy loss. Any questions so far? Okay, so if I would like to sum up this slide, I say that shear stress equals to gamma RS. Very important. Shear stress in uniform flow is gamma RS. What is the R? Hydraulic radius. What's the S? Slope. Gamma is density. This is something that you should know it very well and memorize it. But if the exam is in person, not online, you need to memorize. Okay, in uniform flow, slope of the water surface and channel bottom is the same. I repeated that. So water surface is parallel to channel bed. We know that, we talked about. So water depth remains constant. Yep, we know it. It is called normal depth. So when during this course I said this is normal depth, what does it mean? Normal depth is a depth of flow in uniform condition. Okay? When we have uniform flow, the flow depth is constant or remains constant at the entire length of the channel. It is called normal depth. Here this figure shows you again, this is my hydraulic grid line flow surface. This is my distance. In previous section I said delta x. This is L. Okay, L. It cannot be an element. It can be a big length. Similar to the pipe flow energy equation, we have pipe flow. I already in the fluid mechanics we have this Darcy-Weisbach formula to calculate energy losses. Lambda is Darcy-Weisbach factor. L length of the pipe. V is average velocity. R is also hydraulic radius. Sorry, R is cross-sectional radius of a pipe, and V 2G, you know that V square over 2G is a kinematic velocity or kinematic energy. Rearranging it into we extract V from this Arcev-Weisbach formula. It gives us a square root of 2G over lambda R HF over L. So here we have HF over L. What is HF? Actually, HF, what is HF? Is energy losses, yes? HF is losses. And here, from here to here is HF for this length, energy losses. So if you divide this length, HF, over L, what does it mean? It means the slope of hydraulic grade line, yes? Because tangent theta, for if it is my theta, this is my theta. Let's check, maybe by writing it could be better explained. We said our theta is like always is this. Am I right? This is our theta, or angle of the bed. But in uniform flow, we know that theta equals to this theta. Yes? So this is HF. This is HF. What is the tangent of theta? HF, or front over the side. Tangent theta. Sorry, sine of theta. We said that slope equals to sine of theta. Sine of theta. HF over L. Therefore, we can say that sine of theta, HF over L, it is what? It is the slope of the hydraulic grid line. This slope already shown by S. Okay. Now here we showed with another parameter S0 over L, which is the slope of the hydraulic grid line. I said all, and I wrote here there are in parallel together. Even bed is in parallel to the hydraulic grid line. Therefore, I can say that what? S equals to what happened? Equals to S0. Yes. Therefore, the slope of the bed equals to slope of the hydraulic grid line. So what you should know, S0 is always called slope of bed. Slope of bed, and it is equal to slope of the water surface line. So in this formula, I can replace this term, the HF over L. I can replace HF over L. How to, let me, okay, I raise it. I can replace HF over L with S0 and S0, and I can define another parameter with the name of C, which equals to a square root of 2G over lambda. I have 2G over lambda here. So instead of 2G over lambda, I'm writing C, and instead of this HF over L, I'm writing S0. I have also R. Therefore, velocity in this cross section can be calculated by V equals to C times square root of R times S0. These calculations first time was done by Chezy in 1775, and therefore we can use it for calculation of average velocity in uniform flow condition. Okay, so what is the C? C is called Chezy constant, equals to 2G over lambda. What is the lambda? Lambda in fluid mechanics, lambda was friction factor. this is a parameter, we don't know it. What is it? We don't know. Okay, based on the different characteristics of the channel, it can vary. But we know G is gravitational acceleration, 2 is constant. C, therefore, in Chezy formula, C is unknown because lambda is unknown. R here in natural channels are hydraulic radius, but don't forget that in pipe it was actually it was radius of the pipe, but it is equal to hydraulic radius. If you calculate for a pipe, it gives you exactly R. So R is our hydraulic radius, radius, and we have S0, which is the slope of the channel. These are R and slope are at hand, are known. C is unknown because we don't know lambda. Therefore, using Chezy formula, as shown again here, we can calculate velocity of flow in uniform channels. C is called Chezy coefficient and is a function of hydraulic radius and channel roughness. Yes, I said characteristics of a channel, and it is, we say here is channel roughness. You know, it depends on type of channel or type of canal. You know, for canals we can have canals made by stone, made by concrete, made by wood, or in natural channels it can be the soil, the bottom of the channel can be from fine aggregates, coarse aggregates, lots of rocks and stones. In some cases, it can be only clay with low roughness, or we can have such a vegetation cover at the bed, some trees, trunks, logs within the river. This increase the roughness and change the roughness. Therefore, we know that C is a function of lambda or function of roughness. Therefore, velocity based on Chezy form is a function of, is not only function of slope, physically meaning, physically gives a sense. Velocity is a function of slope, is a function of hydraulic radius, means let's say something like depth of flow. It gives a sense, and roughness. It gives also the sense. When we have higher roughness, you cannot, or water cannot move in higher velocity. And it can be said that higher the roughness, lower the velocity. C is not a constant and depends on the Reynolds number and boundary roughness. Yes, but you know, in fluid mechanics, we use Reynolds number. In hydraulics, we say boundary roughness or simply roughness. Okay, Reynolds number. Here we have some details about Reynolds number. And your book starts to review Reynolds number from pipes that we already know that Reynolds equals to rho v r over mu, or in fluid mechanics we said rho v d over mu. Mu, d is depth, sorry, diameter, rho v d over mu. Mu is viscosity, you know, it's viscosity or dynamic viscosity. Rho is density of water. R is hydraulic radius. Hydraulic radius equals to diameter of the pipe, over V is mean velocity at cross sections. And we said that if the, actually this values are varies in different texts. You remember we talked about laminar and turbulent flow, and when the flow is, actually this is these values are for canals, in canals, okay? If Reynolds value for a canal is less than 500, we say laminar flow. If less higher than 1000, it is turbulent flow. But anyway, these definitions is not useful in practice, because in natural channels we always have turbulent flow. Laminar flow cannot find in natural channels in practice. So let's talk about boundary roughness. These figures show you different kind of possible roughness. You see here roughness should be lower than roughness of here and even here. For example, let me ask you, assume that this is our formula and we are going to calculate velocity of flow in these three kind of channels. Okay, for the constant slope in all these three rivers and in this canal, the slope is constant and water depth is constant. Also, you assume that all three are uniform. Assume it are uniform. It is clear that this one and this one is not uniform definitely, but it could be, this could be uniform. But assume three are uniform, because we are uniform and because we are going to calculate velocity with the Chezy formula. In which channel velocity could be higher than the other? Or do you think all the velocity are the same, because I told slope is constant and depth is constant, or hydraulic radius is the same?
First picture has more velocity.
This one?
Yes,
Why?
because C constant is low for other.
C is lower.
Yes.
Here is lower or higher?
I mean C is in the second picture is higher.
You are right. C is higher here. So C is higher, you mean that roughness is higher. So if C is higher, velocity should be higher also. Am I right?
Yes, true. But roughness is friction, so velocity cannot be more than first picture.
Let's come back here. Look, lambda, you can say lambda is higher, therefore C is lower. Am I right?
Yes, sir.
Lambda is higher. You got the issue. You got what I'm looking for. But here in this picture or in this picture, C is not higher. Lambda is higher. As you corrected yourself, roughness is higher. Therefore, C is lower. Therefore, velocity here is lower. Or we can say that in this canal, roughness is lower than these two canals. If roughness is lower, therefore Chezy coefficient is higher, because roughness and Chezy coefficient has negative direction, negative relation to each other, or adverse relationship. Therefore, velocity is higher. So your friend guessed that roughness in these channels is higher than this one. How he guessed? You without thinking of some of the things written here, you can correctly guess. But what was in the back of your mind? Actually, you thought about bed material. These are bed material, for example, stone, rocks, grassland, trees. These are all bed material. And in bed material, we have different features like D15, D85, KS, Z0, NG. These are some features that you might are familiar with them from soil mechanics course. For example, D50 means the diameter of these stones, these which 50% are less than that diameter. Relative roughness. We also have relative roughness. H means depth of the flow at any cross section over D15. This is another parameter. Or sediment transfer. These are called sediment. These are bed load. We say this is bed load because these are very massive stones and rarely move. And if they move only by sliding on the bed. This is called bed load. This is also called sediment. You know, sediment. We have sediment, small particles that moves in water is called sediment. Bed form also can increase or decrease roughness. When we have straight channels, we have these meandering one like a sine function, you know, meandering. You know, it has several bends along the channel. You see, water moves here, then moves here, then moves here. Bed form or more complex bed form or deviation from a straight line increases the roughness. Vegetation, you see these are vegetation increases. It is like an obstruction. Vegetation, a tree is, these are obstructions. Even stone is an obstruction in front of the, as I told, stumps, logs, boulders, bedrock, outcrops, etc. Variation in channel width and depth. Yes, variation and in the width, you know, you remember me in hydraulics, we had from fluid mechanics, we had, for example, a sudden decrease, a sudden increase in the diameter or change in the diameter. These are variation in channel width and depth. And channel curvature, as I said, meanders. Channel curvature is called meanders, and also sinuosity. Sinuosity shows how your channel has how its curvature varies by the length. Anyway, so many factors, but you are not responsible to go to find those factors and to calculate the roughness. This is a bit topic of detailed investigations by river engineers, and for different kind of channels, bed materials, roughness coefficient or C coefficient will be given you from the standard tables, and we will see here. And I will introduce you a new roughness coefficient, which is called Manning roughness, which is more useful in practice to calculate velocity. So again, in uniform flow, we said that velocity can be calculated using Chezy formula. In Chezy formula, we should know the channel slope, we should know the hydraulic radius, and we should know the Chezy coefficient. We said that Chezy coefficient is a function of roughness, but adversely proportional with the roughness. More roughness, less Chezy coefficient. So one of the practical formulas to calculate Chezy roughness is to use this formula, where C equals to R to the power of 1/6 over N. What is the N? N is called Manning roughness. N is called Manning roughness. or Manning coefficient. And the Manning coefficient already provided in different textbook for different channels. For example, for a river where the surface are the earth, n can vary between 0.02 to 0.025. This is Manning roughness. If the surface is gravel, you see the roughness increases. For unlined canals, man-made channels, okay? Unlined, it means that you only digged and left it. There is no, for example, lining like concrete layer. When you line something, it makes you make it less roughness. For unlined canals, you see, n varies between 2 values. For rock varies this. For lined canals, if your lining material is concrete, n decreases significantly to be in the range of 0.01 to 0.017. Okay, the full length of for different conditions, you can go to different hydraulic books, like one written by Wendy Cha, Open Channel Hydraulics, and the range is given. So we can select n from the table, come back to this formula to calculate c, then use Chezy form to calculate velocity. Is it clear? So let's have an example to see how we can use Chezy formula to calculate velocity in a uniform flow. The example here says a rectangular concrete drive channel, man-made channel, canal, was constructed to conduct water to a small hydroelectric power plant. Concrete of both bed and walls, you know, we have bed and walls and rectangle. Okay, we have this cross section is rectangle of the channel has been done in a current way. It means that in a current way, in the way of the motion. It means roughness should be low, not high. With the channel bed B equals to B. You remember bed width, B channel bed or upper bottom width equals 2 meters. Longitudinal slope of channel bed I equals to 0.6%. I0, we set S0, for example. In our book, we wrote slope with S given 0.6%. What discharge will flow to the hydropower plant, supposing that flow in the channel is uniform, okay? It means that uniform, so we can use Chezy formula. Depth of water in channel should be Y0 equals to 0.21. Y0 is what? Is our normal depth, yes? Because in uniform flow, we always have, or we say that the depth of uniform flow is Y0 or normal depth. During this course, when I wrote Y0, when you see Y0 or YO, it means normal depth. So in this question, we have normal depths, we have slope, we have bed. We know the cross-sectional is rectangle, bed width, Y0, it gives you cross-sectional area. It gives you hydraulic radius at the same time. This information, the slope is at hand, and you are looking for what? Discharge. Okay, how we solve it? Let's see how we solve it. Rectangular area. And we know that the concrete, the section, you know, this is a concrete channel, concrete and lined with concrete. Therefore, to calculate Manning roughness or to find Manning roughness, we should use this information. Okay, let's see how we should start. Rectangular area. Area equals to b times y, given already. 2 times 1.2 gives you 2.4 square meter. Weighted perimeter for rectangular cross section equals to bed width plus 2 times of depth of flow. It could be 4.4 meter. You need to calculate hydraulic radius. A over P equals to A over P gives you 0.5. So you have hydraulic radius. Remember this formula. You calculated R. You need to calculate S0. What is the S0 already given? 0.6%. But 0.6%. We should change it to the this way. S0 equals to 0.0006. It means 0.6%. So S0 is at hand, and now the turn is to calculate Chezy coefficient. And after calculating Chezy coefficient, I can calculate velocity. If I have velocity, I already have area. I can calculate Q by area times average velocity. Never forget, when I say velocity, all are average velocity. So to calculate C or to find coefficient C, I have this formula already talked about. 1 over n times r over 1, 6. What is the n? Monin coefficient. Monin coefficient for concrete, I need Monin coefficient for concrete line channels. Let's go to previous slide and find it. Concrete line Monin coefficient, something between 0.02 and 0.017. And the question says that the lining is in the direction of flow. It means that high quality lining, you know. Therefore, we can go to somewhere average between 0.12 and 0.17. You see that in this example, we used 0.14. Therefore, I have my n, I have hydraulic radius already calculated from here. And this is a constant exponent I have here. Therefore, coefficient of the Chezy should be 64.5. And it has its own dimension. And now you have C, you have A, you have R, you have S0. You can calculate discharge in this way. So discharge of flow, of uniform flow in this canal equals to 2.8 cubic meter per second. Any question? Okay, no question. And here I have another example. Now my canal is not a simple rectangular canal. I have here a irregular. This is irregular or a compound channel. This is a kind of compound channel. Here you see that I have two cross sections, one trapezoidal, for example, and one rectangular. And the question says that open channel as shown, bed slope is given 69 per 1584. It means that for this is for 69 meter drop, we have such an increase in length, 1584 increase in length. Find the flow rate. Flow rate means discharge. Again, flow rate means discharge using Chezy equation. And in this equation, you see that the complexity comes back to the calculation of cross-sectional area and only cross-sectional hydraulic radius, because C already given. Therefore, if I can calculate velocity, then I can calculate discharge easily, because area, cross-sectional area, can be calculated. Okay, we see that, for example, depth of flow is in this rectangular section equals to 0.72, but it is 2.52 in this part. And let's see how we should answer this question. The question says that use Chezy formula. We know that equals V equals C square root of R times S. You see here, instead of hydraulic radius, instead of R, written RH. This is the same thing. I collected these examples from different texts. Therefore, you see different kind of names or letters are used to symbolize the same parameter. Okay, let's calculate cross-sectional area. What is the cross-sectional area here? The summation of this trapezoid plus this rectangle. It gives you cross-sectional area. Then we need weighted perimeter. Where is our weighted perimeter? This is our weighted perimeter. You see from here to here to here to here and to here. You should add all these lengths to calculate weighted perimeter, and I already calculated equals to 177.18 meter. You have area, you have weighted perimeter, therefore hydraulic radius can be easily calculated. A over P, and velocity equals to what? C already given, square root of R hydraulic radius, that's my hydraulic radius, R times S. S, what is S? You can easily slope by dividing these values together. Let's see, 69 over 1,584, and this is maybe you check at home. Maybe this point, O point, should not be appear here. We can calculate without O point 0. If it is, it gives you without O point, it gives you this answer. We should correct them here. If otherwise, this one should be corrected. Anyway, it gives you S0 already given. Question gives you, and you have velocity, you have area. You can calculate the discharge. Here you see that I simply calculated area and velocity by adding different sections. First, area and weighted perimeter, then calculate hydraulic radius. Actually, this is not always true, and in sometimes we have to separate cross sections first, then calculate hydraulic radius for different parts. For example, hydraulic radius of this section definitely will be different with the hydraulic radius of this section. What does it mean? It means that you should calculate velocity here separately. Therefore, velocity for here separately. Then you can calculate discharge of here separately, discharge of here separately, and then you can add together. Definitely, it gives you another answer than this one. And the second method that I explained, separate the compound channels to different regular channels, calculate discharge at separated zones, then add together. It is correct way. But when this separation does not provide higher accuracy, and we simply calculate one hydraulic radius, as you saw here in this, maybe it gives us the answer close to the real value, close to the correct one. It is also acceptable. But this solution, as you see here in this example, this is approximation. Definitely the real discharge is not this one, because we approximated one hydraulic radius for this cross section. In the next examples, I will show you how we calculate discharge for different regular sections and how it gives us more correct answer. So I think I can give you 10 minutes break, then we can continue for a half hour. Is there any question?